Hey guys, today I'll be talking about the lecture 2025 Physics Nobel Prize Explained by Professor Brian Kennedy. So pretty much what this lecture was about is it broke down the science between this year's Nobel Prize in Physics, which was, as we all know after listening to the lecture, was awarded to John Clark, Michel Devoret, and John Martinis for pioneering experiments that, it revealed quantum behavior in superconducting circuits. So pretty much those are circuits that are big enough to see, but still act like quantum particles. So one thing that I didn't know that I learned from this lecture, honestly, I didn't even know what a superconducting circuit was. And one of the biggest things I learned was that macroscopic devices, which are things you can actually see with the naked eye, they can behave according to quantum mechanics. I already knew that electrons and tiny particles follow quantum rules, but I didn't know that superconducting circuits could show quantum tunneling, quantized energy levels, and coherent superpositions. Another insight that I have was how important Josephson junctions are. They're pretty much these tiny superconducting sandwiches. Then they're like artificial atoms. So these are pretty much the foundation of many quantum technologies today, like superconducting qubits. And I also didn't know, I honestly didn't know who Clark, Devoret, or Martinis were. So it was really eye-opening to see, how important these people are to the physics space. What I learned that I already knew that superconductivity allows electrons to move without resistance, and that this is really, really important for highly sensitive measurements. I also knew that quantum computing uses qubits that can be used in multiple states at once. But what the lecture pretty much did for me was it connected these ideas for me. I understood, the general concept before, but, this lecture was able to show me how, these different concepts came together in real experiments that, won the Nobel Prize. What sparked my curiosity was how these engineers can they can make these circuits that behave like quantum systems, but these quantum systems are controllable. So it's like designing your own atom. The idea is really, really insane. So it's the lecture pretty much made me wonder how far can we push this newfound discovery. We've never been able to make this type of thing before. And how could we scale these actual circuits into full quantum processors? So pretty much scale from this small kind of atom type structure into a way bigger, way more powerful processor. And how there could be an improvement to technologies like MRIs or secure communications or sensors. So when he talked about these early experiments from the 1980s and how they evolved into the companies that they are today, or how they evolved into these devices that companies use all the time, it just made me want to look into how the engineering works with that, and how this connects to my own area of study. So I'm electrical engineering. So, obviously circuits, a superconducting circuit is very, very relevant to the electrical field. And I mean, it shows just that when you're in engineering or in innovation, it just shows how a breakthrough in the lab can lead to, such real application. So the Nobel Prize was obviously a perfect example of this. It began as a curiosity, became an experiment, which became a breakthrough, and now it's the heart of quantum computing, which is just insane to me. And did I follow up outside the lecture? Yeah, after the lecture, I looked a little bit more into the Nobel Prize from this year and the scientists that were involved. I watched a short little Reuters video describing the award, and I read an article about Clark, and what he did on superconducting quantum interference devices, or SQUIDs. And, these devices can pretty much detect really, really tiny magnetic fields, so it's really, really interesting. So in conclusion, the lecture helped me understand why the Nobel Committee recognized these researchers. Their work proved that, quantum mechanics doesn't just belong in the microscopic world. It can shape real devices, and it has real world use in our everyday lives. It was a really, really interesting lecture, and I just really want to learn more about the engineering behind quantum circuits.